Part 1. The prototype arrived at the Beretta testing facility in Gardone Valtrompia on a January morning in 1972, packed in waxed canvas and surrounded by technical documentation that weighed more than the equipment itself. Vittorio Valle stood in the clean room, walls painted institutional white, fluorescent lights reflecting off polished concrete floors, and lifted the device from its case. The scent of protective oil and fresh-cut steel filled the space. The AR70 measured 955 millimeters from buttstock to muzzle, its stamped steel receiver showing faint tool marks from the hydraulic press. Valle's hands moved across the surface, checking tolerances at the barrel junction, testing the lateral play in the folding stock mechanism, confirming the bolt carrier moved freely on its guide rails. The unit weighed 3.5 kilograms unloaded, heavier than American designs, but significantly lighter than the BM-59 it was meant to replace. Valle had spent 18 months refining this configuration. The gas system positioned above the barrel, a rotating bolt with 7 locking lugs, a fixed gas regulator that eliminated adjustment complexity, and a trigger mechanism offering different firing modes without burst limiters. Every component reflected a deliberate choice between sophistication and reliability, between advanced materials and proven manufacturing techniques. He inserted an empty magazine, pulled the charging handle, and felt the bolt slam forward with mechanical certainty. The action cycled smoothly, the recoil spring compressed and released without binding. The selector clicked between positions with tactile precision. These were the baseline confirmations, the mechanical grammar that preceded actual testing. But Valle's attention kept returning to the muzzle. The barrel threading represented his core engineering philosophy made physical. Right-hand rifling at 1 in 12-inch twist. Muzzle threads cut at 0.5 inches by 28 threads per inch. Left-handed to prevent loosening under operational stress. A spring-loaded detent system allowed muzzle attachments to be swapped by hand in seconds, flash hiders for low-light use, compensators for recoil management, and specialized adapters for training exercises. The Italian forces had requested a single platform capable of serving mountain troops, urban units in close-quarters environments, and training battalions conducting exercises. Rather than designing 3 separate variants, Valle had created one system with field-swappable muzzle components. The threading was the physical manifestation of modularity before that concept dominated mechanical engineering. Outside the testing facility, winter wind moved through the Valtrompia Valley. Inside, Valle began the initial function checks that would determine whether 18 months of design work had produced a viable service tool or an expensive prototype destined for archival storage. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Part 2. The pressure on Valle came not from ballistics or ergonomics, but from industrial capacity. In 1972, Beretta possessed extensive expertise in machining steel and assembling precision mechanisms. The company had manufactured hardware since 1526, and its factories in Gardone Valtrompia represented centuries of accumulated metallurgical knowledge. But the company lacked the advanced polymer molding infrastructure and exotic alloy processing capabilities that characterized American or German defense contractors. Valle understood this constraint intimately. He had toured manufacturing facilities in Connecticut and Stuttgart, observed the injection molding systems that produced polymer components, and studied the cold forging techniques that created lightweight aluminum parts. Beretta could replicate some of these technologies, but not quickly and not at competitive costs. Any design that required significant capital investment in new production equipment would face bureaucratic delays and budget scrutiny. So Valle had designed the AR70 around existing capabilities. The receiver used stamped steel, a material Beretta's hydraulic presses had shaped for decades. The lower receiver, trigger housing, and magazine well were machined from aluminum alloy using conventional mills and lathes. The stock folded on a simple steel hinge, requiring only basic welding to attach. Even the 30-round magazine derived from existing patterns, avoiding the expense of developing new tooling. This approach created its own constraints. Stamped steel receivers weighed more than polymer alternatives. Aluminum components required careful heat treatment to prevent stress fractures. The folding stock mechanism added lateral width that complicated storage in vehicles. Valle accepted these limitations as the cost of rapid production readiness. The Italian Ministry of Defense had specified a replacement for the BM-59 by 1973, a deadline that left no room for extended research and development cycles. The service needed a platform that could be manufactured immediately using existing infrastructure, serviced by technicians trained on traditional mechanical systems and operated by personnel familiar with conventional maintenance procedures. Valle's design philosophy emerged from this temporal constraint, incremental synthesis rather than revolutionary innovation. The gas system borrowed proven principles from the Soviet lineage. The rotating bolt followed patterns established by the American AR-15. The trigger mechanism simplified concepts from the Belgian designs. Nothing in the AR-70 was unprecedented. Everything was deliberately familiar. This conservative approach carried risks. Procurement officers often favored innovative features that justified budget expenditures. Technical journalists praised cutting-edge materials and unconventional configurations. Valle's straightforward design offered no dramatic selling points, just reliable operation through mechanical simplicity. But he had one engineering detail that elevated the entire platform: the muzzle threading system. By allowing field-swappable devices without specialized tools, Valle transformed a single unit into multiple operational configurations. A mountain unit could install flash hiders before a night patrol and remove them afterward. An urban response team could attach compensators for close-quarters precision. A training battalion could add specialized adapters for exercises without sending hardware to maintenance facilities. The threading decision required precise machining, left-hand cut at exact tolerances to prevent loosening under vibration, but used conventional lathes that Beretta's machinists operated daily. It added negligible weight, created no moving parts that could fail, and required no maintenance beyond periodic cleaning. Valle had found the intersection between manufacturing capacity and operational flexibility. Part 3. The gas-actuated operation of the AR-70 followed physical principles that had governed hardware design since the late 19th century, but Valle's implementation reflected specific choices about reliability versus complexity. When a cartridge activated, propellant gases expanded behind the 5.56mm projectile, accelerating it down the 450mm barrel. After the projectile traveled 230 millimeters, roughly halfway, a small port in the barrel's upper surface allowed gases to exit into a steel cylinder positioned directly above. These gases drove a piston rearward at approximately 400 meters per second. The piston struck the bolt carrier, a machined steel component weighing 285 grams, transferring kinetic energy that forced the carrier backward along guide rails in the receiver. As the carrier moved, cam slots machined into its interior surface engaged corresponding pins on the bolt head, rotating the bolt counterclockwise to unlock 7 locking lugs from recesses in the barrel extension. Unlocking occurred across the first 6 millimeters of carrier travel, a timing sequence calculated to ensure internal pressure had dropped to safe levels before the bolt separated from the casing. Valle had specified this distance through iterative testing. Too short and residual pressure could damage the components. Too long and the action cycled sluggishly. With the bolt unlocked, the entire carrier assembly traveled rearward 115 millimeters. The extractor claw gripped the spent casing, pulling it from the chamber. An ejector pin struck the casing head, propelling it laterally through an exit port on the right side of the receiver. Simultaneously, a recoil spring compressed inside the stock, storing energy for the forward cycle. At full rearward travel, the carrier stopped, the spring rebounded, and the assembly accelerated forward. The bolt face stripped a fresh cartridge from the magazine, drove it into the chamber, and the cam slots rotated the bolt clockwise to lock. The internal hammer remained ready if the trigger was released. If the trigger remained depressed in continuous mode, the hammer fell immediately to initiate the next cycle. The entire cycle completed in 0.096 seconds at a cyclic rate of 625 rounds per minute. Fast enough for sustained operation, slow enough to maintain control during bursts. Valle's critical design choice involved the gas regulator. Most contemporary designs featured adjustable gas systems that allowed users to increase or decrease gas pressure based on temperature, fouling, or environmental conditions. These adjustable systems added moving parts, required periodic adjustment, and introduced potential failure points. Valle specified a fixed regulator, a simple orifice drilled to precise dimensions that could not be altered without machine tools. This decision eliminated user error and mechanical complexity, but required careful calibration during manufacturing. The orifice diameter of 2.8 millimeters provided sufficient gas pressure to cycle the action across temperature ranges from 40 degrees to plus 150 degrees and ammunition variations of plus 15% from nominal pressure. Testing had confirmed this fixed setting worked reliably, but it meant users could not compensate for extreme conditions or severely fouled barrels. Valle accepted this limitation as preferable to mechanisms that could be misadjusted in the field. The gas piston itself was chrome-plated steel, 8 millimeters in diameter, with a captured return spring that kept it pressed against the bolt carrier. Residue from propellant gases accumulated on the piston head, but the chrome plating prevented adhesion, and the spring pressure ensured consistent contact. Technicians could remove the piston for cleaning by driving out a single steel pin. No proprietary tools required. This maintenance accessibility extended throughout the unit. The bolt carrier group disassembled into 5 components with 1 pin removal. The trigger mechanism could be lifted out of the lower receiver after pushing 2 retaining pins. The barrel was pressed into the receiver and could be replaced by armorers with a hydraulic fixture, though not in field conditions. Valle had designed every connection point to be serviced with basic implements: punches, pliers and cleaning rods, no Allen keys, no Torx drivers, no calibrated torque wrenches. The AR70 assumed its users would be individuals with mechanical aptitude but not specialized training, operating in environments where sophisticated tools might not be available. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Part 4. The first endurance test occurred in March 1972 at a testing range outside Brescia. Valle watched from an observation shelter as technicians subjected 3 prototype units to accelerated wear cycles, operating each 10,000 times over 72 hours, pausing only to allow barrels to cool and to address occasional mechanical interruptions. The test protocol used standard 5.566 45mm NATO ammunition, firing in bursts of 30 rounds, followed by magazine changes. Technicians recorded every mechanical failure. By design, they did not clean or lubricate the units during the test. The mechanisms accumulated carbon residue and brass particles until the systems became visibly dirty. Unit 1 experienced 11 malfunctions over 10,000 cycles, a failure rate of 0.11%. Most failures occurred after cycle 8,000, when residue buildup on the gas piston reduced stroke energy. Unit 2 performed similarly, with 13 malfunctions. Unit 3 failed twice in the first 500 cycles due to a cracked extractor, then ran without incident after the component was replaced. These numbers fell within acceptable standards. Contemporary designs typically exhibited failure rates between 0.1% and 0.3% under similar conditions. Valle reviewed the malfunction reports carefully, noting that most failures involved extractors and ejectors rather than the gas system or bolt mechanism. The core operating principles were sound. The peripheral components needed refinement. The more revealing test involved the muzzle attachment system. Technicians operated Unit 1 with a flash hider installed, then swapped to a compensator, operated it again, and finally swapped to a training adapter for blank cartridges. They repeated this cycle 5 times, installing and removing attachments without tools, relying only on the spring-loaded detent mechanism. After 3,500 live cycles and 2,500 training cycles, the muzzle threading showed no deformation. The detent spring maintained consistent tension. The muzzle attachments installed and removed smoothly with hand pressure. No loosening, no stripping, no thread damage. Valle's left-hand threading specification had worked precisely as calculated. The attachment actually tightened slightly under vibration rather than backing off. This result validated the core engineering premise. A single platform could serve multiple operational requirements without requiring specialized variants or workshop-level modifications. A mountain unit could reconfigure equipment for different missions in minutes. A training battalion could convert units from live use to blank ammunition without sending them to secondary facilities. But the endurance test also revealed limitations. The stamped steel receiver showed stress fractures near the magazine well after 9,500 cycles, acceptable for a prototype, but concerning for extended service life. Valle noted the fracture locations and made adjustments to the stamping die geometry, adding material thickness at high stress points. The modifications added 120 grams to the weight, but eliminated the cracking in subsequent tests. The aluminum lower receiver exhibited wear where the trigger mechanism contacted the housing. Valle specified a harder aluminum alloy and added a thin steel insert at the wear point. Again, a weight penalty of approximately 50 grams resulted in the elimination of the failure mode. These iterative refinements characterized the entire development process. Valle did not pursue radical redesigns, but made incremental adjustments based on empirical data. Each modification addressed a specific observed failure without altering the fundamental operating principles. By June 1972, the AR70 had achieved a reliability profile that met official procurement standards. Part 5. The revelation about muzzle threading came not during formal testing, but during a field evaluation with mountain troops in the Dolomites in October 1972. Valle accompanied a detachment of 30 personnel conducting high-altitude exercises at elevations between 2,000 and 3,000 meters. The personnel carried pre-production AR70 units equipped with flash hiders for low-light use. On the 3rd day, the unit conducted a dawn patrol, requiring them to descend from a bivouac site to a valley village, conduct simulated reconnaissance, then climb back to altitude before nightfall. The flash hiders, necessary for low-light operations, created additional blast and recoil during daylight use, making precision at extended ranges more difficult. A junior officer approached Valle during the midday rest period. "Can we remove these?" he asked, gesturing to the flash hider. "They're useful at night, but problematic during the day." Valle handed the individual a spare compensator from his equipment bag. "Try this," he said. The officer unscrewed the flash hider by hand, the spring detent clicking as it released, and threaded on the compensator. The entire exchange took approximately 15 seconds. No tools, no adjustment, no technical oversight required. The individual tested the unit at a target 300 meters downrange. The compensator redirected gases upward, counteracting upward movement. His grouping tightened noticeably compared to the previous configuration. "This changes everything," he noted. Valle realized the officer had articulated the central design philosophy without understanding its engineering implications. The muzzle threading system transformed the AR-70 from a fixed configuration tool into an adaptive platform. Users could optimize their equipment for specific tactical requirements, low light concealment, recoil management, or training without dependence on maintenance facilities or specialized personnel. This capability emerged not from advanced materials or electronic systems, but from precise mechanical threading. The 0.5-inch by 28 thread per inch specification, left-hand cut, represented Valle's understanding that modularity did not require complexity. A simple, threaded interface, manufactured to exact tolerances, provided operational flexibility that more sophisticated systems could not match. The field evaluation continued for 2 weeks. Personnel swapped muzzle attachments based on mission requirements, cleaned the threading with standard brushes, and installed devices by hand without torque wrenches or calibration equipment. The system never failed. Attachments never loosened during use. Threads never stripped or seized. Valle documented these field observations in technical reports that accompanied the formal evaluation data. The reliability statistics mattered: failure rates, cycles between malfunctions, parts replacement intervals. But the muzzle threading system represented something more fundamental, a design philosophy that prioritized user autonomy over centralized logistics. Traditional doctrine assumed configuration occurred at the depot level, with technicians modifying equipment for specific units or missions. Valle's threading system decentralized this process. Individual users could reconfigure their tools based on immediate tactical requirements, then reconfigure again when circumstances changed. This approach aligned with emerging theories in the early 1970s. Global events had demonstrated the importance of rapid adaptation to fluid situations. Fixed configurations optimized for specific scenarios often proved inadequate when circumstances shifted. Valle's solution was mechanical rather than doctrinal. Create a platform flexible enough to accommodate unpredictable requirements. The threading decision also reflected industrial pragmatism. Manufacturing 3 different AR-70 variants would have required 3 separate production lines, 3 inventory systems, and 3 maintenance protocols. A single unit with swappable muzzle components required 1 production line and a small inventory of standardized parts that users could manage themselves. Part 6. The Beretta AR70 entered official service in 1972 and remained the standard infantry platform until the AR70-90 revision in 1984. During those 12 years, it equipped mountain brigades in the Dolomites, security units in urban centers, and training battalions throughout the country. The design never achieved mass international adoption. German and American derivatives dominated global markets, but it served its intended purpose, providing local forces with a reliable, maintainable platform manufactured using existing industrial capacity. Valle's muzzle threading system became the defining feature that differentiated the AR-70 from contemporary designs. Where other units required workshop-level modifications to change attachments, the AR-70 allowed users to reconfigure equipment in seconds. This capability proved particularly valuable for security units conducting both urban patrols and rural operations. They could install compensators for precision during the day and swap to flash hiders for night missions without interrupting their pace. The broader engineering lesson concerned constraints as creative opportunities rather than obstacles. Valle could not access advanced polymer molding or exotic alloys, so he designed around stamped steel and aluminum, materials the company had worked with for decades. He could not rely on sophisticated gas regulation, so he specified a fixed regulator, calibrated for broad conditions. He could not produce multiple variants within the timeline, so he created one platform with field-swappable components. Each constraint generated a design decision that prioritized mechanical simplicity over technological sophistication. The result was not the lightest tool, not the most innovative or the most advanced, but a platform that could be manufactured immediately, maintained by users with basic mechanical knowledge, and adapted to diverse requirements without specialized support. The muzzle threading embodied this philosophy in physical form. Left-hand threads, precisely cut to prevent loosening under vibration, a spring-loaded detent that required no tools to operate, universal compatibility with various attachments. The threading itself cost approximately 12 minutes of lathe time per barrel and added no weight. But it transformed the AR-70's operational flexibility. By 1984, advances in polymer technology and manufacturing processes had rendered the steel and aluminum approach obsolete. The AR-70-90 revision incorporated modern materials, improved ergonomics, and enhanced modularity. But the muzzle threading system remained unchanged. Valle's original specification continued to serve because the fundamental engineering principle remained valid. Precision mechanical interfaces provide reliable modularity without complex systems. Valle retired in 1989 after 37 years with the company. He had designed several systems during his career, but the AR-70 represented his most complete expression of engineering philosophy. When asked late in life what he considered the most important feature, he did not mention the gas system or the folding stock or the steel receiver. He pointed to the muzzle threads. Everything else was compromise, he said. The threading was intention. The AR-70 survives in technical collections and occasional service use, a reminder that sophisticated engineering sometimes means knowing which complexities to avoid. Valle understood that a design optimized for industrial capacity, mechanical simplicity, and field adaptability would outlast those designed for performance specifications alone. The threads at the muzzle, 0. 5 inches by 28 threads per inch, left-hand cut, precisely machined, represented engineering as synthesis rather than innovation, proving that the tools and materials available define what can be built as surely as theoretical ideals. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.